So it's my pleasure to introduce Peter Scholze from the University of Bonn. Peter spoke at CDM already in 2012, but since that time, his results have been so spectacular that the organizers wanted to invite him back again to speak on those results. Peter has won since then also a number of prizes, including the Pripico, the Sastro-Ramanujan Prize, the Clay Research Award, the Ostrowski Prize, and the Cole Prize in Algebra. He will speak on locally symmetric spaces and Galois representations.
Thanks. Thanks so much for the introduction, and thanks a lot to the organizers for the invitation to speak. It's a big honor to speak here. So I guess, yeah, the title of my talk is locally symmetric spaces and Galois representations. And I guess really what this is about some kind of higher reciprocity laws. And so in the first talk, I want to give an introduction to what this is about. And so I guess I want to describe some general result, but I want to describe it in the first interesting case where it's a new result. So maybe I wait for people to come. Yeah, sorry. By the way, is this large enough, or should I write bigger? It's good? Okay. People in the front say it's good, so it must be good. All right, so I guess I was saying that, title of my talk is Locally Symmetric Space and Galois Representations, and so in some sense, all I'm saying is about some kind of higher reciprocity laws, and I want to explain some general theorem, and I want to explain it in the first case where it's a new result. And so that case will be a relation between the following two kinds of objects. So one is an object which belongs to some geometry or topology. So it's about certain hyperbolic 3 manifolds known as Bianchi manifolds. And so these were actually already introduced in the 19th century by the differential geometry Luigi Bianchi in, I think, 1892. These quite classical objects. And on the other hand, we have some objects from algebra or number theory, which would nowadays be called Galois representations. But I want to explain what I mean by this and explain that these are probably not as, these are actually quite explicit objects. So what is this about? So it's about the field of algebraic numbers, first of all. So let's consider inside the complex numbers the field of algebraic numbers. So this would be the set of all those complex numbers which satisfy some polynomial equations with rational coefficients. So there exists some n, let's say a1 through an, such that x to the n plus a1, x to the n minus 1. So these are meant to be rational, plus and so on, plus an. And great. So then one can consider this absolute Galois group of Q, which is, it's usually denoted like over Q over Q. But this is just the group of all automorphisms commuting with additional multiplication of these algebraic numbers. So this is a large profinite group. And so what elements of this field do, they probably send complex the unit to minus a complex unit, and they might decide that they send square root of 2 to minus square root of 2, and third root of 7 to third root of unity times square root of 7, and so on. And it's probably not a priori clear that you can somehow extend this to a field automorphism of Q bar, but it's one of the results of Galois theory. And so in Galois representations, you're interested in representations, I guess technically continuous, representations rho of this absolute Galois group into GLN of some field K. And there are many different choices for what this field might be. Maybe most traditionally, you might take the complex numbers. That's what's called an Artin representation. And something that happens there is that the topology of the complex numbers is essentially incompatible with the topology on the absolute Galois group, which is totally disconnected. So any such continuous map will have finite image. More interesting, thus, why I say take QP or an algebraic closure thereof, because the p-adic topology on the QP plays well with the topology on the absolute Galois group, and there are many more such guys. And maybe in the talk, I will also often consider the case just FP bar, which is maybe simpler. And so what does it mean to give such a Galois representation? I will explain what this is in the simplest possible case, or in one case which I will consider later on again. So say you have given a map from the absolute Galois group to GL2 of the field with 3 elements. And let me forget just a little bit of information, namely the central part. So let's go to PGL2F3. Then PGL2F3, you can check, is just the symmetric group on 4 letters. One way to get a map is to observe that PGL2F3 acts on the projective line over F3, which has 4 points, and it gives this isomorphism. And so I guess this means that the absolute Galois group will act on a set with 4 elements. Which a priori has just some abstract elements, but actually Galois theory tells you that you can think of these 4 elements as the 4 roots of some degree 4 polynomial. And so giving such a Galois representation or such a map to S4 is more or less the same thing as talking about some degree quadratic polynomial with rational coefficients. Okay. So these are the objects that will be important. Sorry. And so one standard question that turned out to be a very interesting question that one asks in the field of algebraic number theory is given such a polynomial P of x for which primes P so of course, in general, you can't hope to solve the equation that is 0 in the rational numbers, but you can hope to solve it mod P. So. Solution. And so Gauss famously solved this in the case of quadratic polynomials. So Gauss's quadratic reciprocity says is, I don't want to state it in all details, but he gave a complete answer for all quadratic polynomials. So meaning n is equal to 2 here. I guess the n here has nothing to do with the n here, but anyway. So for example, the thing done very early on is that there's a square root of -1 mod p, so you can solve x squared plus 1 is congruent to 0 mod p. So a priori, you might find it hard to, given a large prime, to figure out whether there's such an x, but actually what Gauss tells you is that you only need to check that p minus 1 is divisible by 4, which is really easy. Or maybe that p is 2. And the major part of algebraic number theory in the late 19th and early 20th century was about generalizing this kind of reciprocity laws to cubic polynomials or things like that. And so what happened then in the early 20th century, and I guess for Q maybe a little earlier, people came up with a complete answer. So this has been generalized to what's called class field theory. Which gives an answer for all such polynomials such that so the Galois group of Q will always act on all the zeros of P. But you ask that it acts through an abelian quotient. So these are the so-called abelian extensions of Q. And so in the case of the rational numbers, so I guess so this works for any finite extension K in place of Q. One thing that's special about Q and a few other fields, so-called fields with complex multiplication, is that you can actually describe the maximal extent. You can describe all the abelian extensions of Q. So in this case, you just have to adjoin all the roots of unity to Q by theorem of Kronecker and Weber. And it was one of Hilbert's problems, which is still open, to extend this to general number fields. But I'm not talking about that. Really? So, so I guess after you understand the abelian extensions, you're trying to understand the non-abelian extensions. And now maybe what I'm to discuss next, maybe the relation to this elementary question I asked in the beginning will be a bit lost, but I hope to come back to it at the end of this talk. I try to make clear how these are, well, maybe make clear that these are some generalizations. So I guess the first such reciprocity law was in the work of Eichler and Shimura, which in the simplest case found a relation between the following kinds of objects. On the one hand, what I call elliptic curves. So I guess these are equations of the form, sorry, oops, y squared is x plus b, where a and b, in this case, I guess, are rational numbers, or q. So these elliptic curves turn out to be, if you're at an infinite point, have a natural group structure in there. The complex points of these are one-dimensional, sorry, are Riemann surfaces of genus 1. Yeah? And so a relation between modular forms of weight 2 so I guess modular forms also appeared in the last talk, but let me briefly remind you. So if they are of weight 2, then you can consider them as differential forms on the upper half plane mod gamma. So what's the notation here? Gamma is a congruent subgroup of SL2 of the integers. Congruent subgroup. So it's a finite index subgroup given by congruence conditions on the matrix entries. And H2 is the upper half plane, so it's the set of all 12 positive imaginary part. And, oops, great. I still have one more backward here. So what I want to say about this, I wanted to draw a picture because later on I will draw a slightly more fancy version of this picture. And so I mean, everybody knows this picture probably. So here's the upper half plane somewhere of 0, 1, minus 1. And then you can draw these half spheres around these points. So these are geodesics in the hyperbolic plane. And then maybe I should use colored chalk. So this color is probably good. And so this kind of region here would then be a fundamental domain for the action of SL2Z. And so in particular, you see, what happens is that there is this translation symmetry. So if f of tau d tau is such a guy, then f of tau is equal to f of tau plus 1, because it's invariant. And so you get a Fourier expansion. You can write this as a sum of a n, I'm assuming some growth condition near infinity, times whatever we'll call q to the n, where q is e to the 2 pi I tau. And I guess in using this, I imposed a slight condition on gamma, but anyway. Okay, so let me remind you how this relation goes in this case. So this takes the following form. So if you have f, which I will assume is of the form q plus a2 times q squared plus and so on, plus an times q to the n, and so on, is the modular eigenform, this is important, of A2. Let me say what it means in a second. Such that the AI are in Q, which actually implies that they are in Z. So eigenform refers to the fact that there are some extra Hecke operators acting on the space of modular forms. It's a large commuting algebra, and you can find simultaneous eigenvectors for this action, and it's supposed to be an eigenvector for this guy. Then there exists an elliptic curve EF over Q. An elliptic curve. Oh, wait, I can mess that up. Such that for almost all P, so what's the relation between this analytic object and this algebraic object? One relation is that you can predict how many solutions there are to this equation that defines this elliptic curve over a finite field. So it's not merely the question whether there is a solution, which will basically always happen, but it's about the number. And this will be, depending on whether you, the infinite point is in here, so it's p plus 1 minus AP. So the Fourier coefficients of this modular form tell you in a miraculous way about the number of points of this elliptic curve over Fp. Oops. All right. Oops. So I don't want to talk too much about Hecke operators in my talk, but you shouldn't actually think about this AP as a Fourier coefficient. It's better to think a bit it as an eigenvalue of a specific operator acting on this modular form, which just happens to be, in this case, just a Fourier coefficient, which makes it easier to compute. But more conceptually, you should think of this as an eigenvalue for some Hecke operator acting on this F. And so what I wanted to say is that in this case, the association taking this modular form to an elliptic curve is actually relatively explicit. So how does this go? So first of all, you use Hodge theory. Hodge theory tells you that if you look at the first cohomology group, H2 mod gamma of this modular curve we're looking at, that, well, this is related to differential forms. So you have the Hodge decomposition where one of the terms is given by differential forms, so, which are way2 modular forms. So this means that if you have your way2 modular form, then there's also somewhere a cohomology class on this guy. But on the other hand, if you look at H2 mod gamma, then as it stands, it's just some complex curve, but actually some complex manifold of dimension 1. But actually, it turns out to be a Riemann surface, so an algebraic curve. And moreover, it turns out to be defined over the rational numbers. At least if I put a small assumption on gamma. And I mean, often, more precisely, when there's just one way two-modular form of this level gamma, it is already this sought-after elliptic curve. So in small examples, that's what happens. In general, you would have to take a piece of the Jacobian. So H2 mod gamma would be an algebraic curve over Q. Its Jacobian is in the BM variety, and using these Hecker bars I didn't talk about, you're able to isolate one elliptic curve summand of this, which is related to this modular form you're interested in. So I guess the upshot is that if you look at H2 mod gamma, then you can do analysis on this guy. And this has something to do with modular forms. And on the other hand, you can do algebra with it, because it's an algebraic variety. And this is related to these elliptic curves. I should also, at this moment, state the theorem of Wiles, Taylor, completed by Brawley, Conrad, Diamond, and Taylor, that all elliptic curves over Q come from such a modular form. One of the major breakthroughs. So, to prove that, it's unfortunately not possible to give any direct recipe of starting with this elliptic curve and producing this modular form. It's a very indirect proof. And so I think at least in part motivated by the story for elliptic curves and modular forms, Langlands came up with a Weiss generalization of the story. So he conjectures a Weiss generalization. That is following. So there's this generalization of the concept of a modular form called an automorphic form on GL2. So here K over Q is any finite extension. And sorry, I meant GLN, any n, or in fact any reductive group if you want. And on the other hand, something which is maybe not totally precise, but some motives of rank n over K. So motive is something which is, on the one hand, supposed to be something like an algebraic variety over K. So such as in this example, the elliptic curve. But on the other hand, it's also supposed to be roughly the same as a representation of the absolute Galois group into GLN QP bar. So in the case of the elliptic curve, what you could do is you could look at its first état cohomology, or more concretely at its state module, which would provide you with such a Galois representation. You can choose a p. So for any p, if I put the right adjectives here, there's some, if you look at irreducible such guys up to isomorphins, they should somehow be in bijection for varying p, which is a very surprising statement a priori. And so I guess in general, if you have an algebraic variety, then you get such a Galois representation by looking at its état cohomology groups. And so the case of GL2 over Q is now large after the work of Wiles et al. And then developments in the periodic Langlands program by Broglie and Comès and others led to the proof of many cases of the so-called Fontaine-Mazur conjecture by Emerton and Keesin. So it's largely known, except for one notable case. They are so-called even Artin representations, so representations of finite image with specific behavior for complex conjugation. And they are supposed to correspond to some mass forms, which we have no idea how to attack. Mass forms of eigenvalue a quarter. And in some cases, by work of Langlands using base change, we have some results, but in general, we know neither direction of this correspondence. Don't see any way of attacking this. All right, but some of you, GL2 over Q is largely understood. And so the next case after that, you could either go to GL3 over Q, which is hard, or to GL2 over a quadratic field, say. So the next case, say, might be GL2 over K, where K is a quadratic field. So K you get by taking Q and joining a square root of some number. And there's one important distinction. If D is positive, the so-called real quadratic case, because there's a real root, that's similar to, turns out to be similar to GL2 over Q. And many of the methods that worked over Q can be generalized to such a real quadratic field. This is because the relevant locally symmetric spaces there turn out to be still algebraic varieties. These are the so-called Hilbert-Blumenthal varieties, surfaces, or you can pass to some forms and go to Shimura curves. Or D is less than 0, so so-called imaginary quadratic case, because the root is imaginary. So in that case, something totally different happens. So it's very different. So let me explain what happens there. So as for GL2 over Q, some of these automorphic forms that we're talking about, there are some functions on some, or forms on some locally symmetric spaces. And so here's a relevant locally symmetric space is well, let's call it X gamma. So this will be a three-dimensional hyperbolic space divided by gamma. I'm running out of talk. Where so gamma, as before, is maybe an SL2 of the ring of integers of K, is a congruent subgroup. And H3 is three-dimensional hyperbolic space, so I don't know, C times the positive reals or something like this. That's three-dimensional hyperbolic space. So I guess these are the gadgets that appeared in the very first Blackboard. These are the Bianchi manifolds. So these are three-dimensional hyperbolic manifolds. If gamma is torsion-free, so I always allow myself to pass some finite index subgroups, so this is really a manifold. You don't have stabilizers. It's not compact. It has finitely many cusps, having something to do with the class number of this imaginary quadratic field. Add the cusps to get some tori, compactifying it. It's a very interesting space. So I guess I want to try to draw a picture. So let's do this. Oops. So just like the upper half plane was some of the space above a line in a two-dimensional space, you can think of this hyperbolic 3 space as a stuff above a complex line in 3 space. So this is some of the complex plane, and somewhere maybe you have 0. Sorry, it's not legible. 1 plus I, and I in the base. And then the analog of these geodesics becomes certain half spheres which you have, which you can draw around these guys. Oops. And now this is tricky to draw. I don't know. Oops. Something like this. Let me try to use colored chalk too. Oops. So, as a fundamental domain looks roughly like this. It's bounded by 4 half spheres. So I guess this is supposed to be a fundamental domain for the action of SL2 of the Gaussian integers. And so in this case, you see some orbifold points, but these would go away if you pass to some finite index subgroup. And I guess the picture looks like just for the modular curve, but 1 dimension higher. In particular, you can see that the picture for the modular curve appears often inside this picture, and this corresponds to some embeddings from the modular curve inside there. However, there's one extremely important difference. So their real dimension is 3. Hence, they have not even the chance of having a complex structure. And hence, a fortiori no algebraic structure. And so this means that the way we've constructed this elliptic curve for GL2 over Q has not the slightest chance of working, because this object is just not related to algebra. All right. So there are also some other differences. So let's look at the first homology group, say, of this guy with Z coefficients. Okay, so it has some free part whose order is the first Betti number of this guy, but then it has some torsion part. And so for the modular curve, what happened is that there actually is no torsion, and you can easily compute the dimension of this space. So there are formulas for the dimension of spaces of modular forms. But this doesn't turn out to be true in this case. And it turns out actually that this, it behaves quite erratically, but it's also quite small. So there's a theorem of Luc from '94 that it's the first Betti number grows smaller than the volume as gamma becomes small. On the other hand, in this case, the torsion part turns out to be extremely big. More precisely, there's a conjecture of Bergeron and Venkatesh, for which there's both a lot of theoretical and experimental evidence that it grows exponentially in the volume. And so I could give you an example computed by Sengun where, for some specific congruence subgroup of SL2 of the integers, which is some small congruence condition, where there is some like 13-digit prime dividing the order of this torsion part. Yeah, but on the other hand, if you somehow go to big imaginary quadratic fields, then also there's a lot of stuff. there's a whole lot of stuff there. Anyway, so if you look at this guy with complex coefficients, and this is described by automorphic forms, by some form of Hodge theory. And so thus, by the Langlands conjectures, we expect to have some motive, and we don't know what this is, but concretely we at least expect to get attached two-dimensional Galois representations. And then there's a question, does this really only work with complex coefficients, or are there these Galois representations also for torsion classes, which somehow do not a priori fit into this framework of the Langlands conjectures about automorphic forms, etc. And people made experiments on that, and it turned out that they could always find such a Galois representation that seemed to be attached to this guy. And so I think the first such experiments were done by Grunewald in the 70s, and a precise conjecture was formulated by Avner in 1990. Maybe in the setting of GLN over Q, but I think it's clear that it should adapt. That given a system of Hecker eigenvalues, or let me abbreviate it. So for any torsion class, for any mod P torsion class, there is an associated Galois representation. Yeah, so I should say, yeah, Galois group to GL2 FP bar. Yeah, so again, you have commuting Hecker operators. So if you have a torsion class, then you can find also many Hecker eigenclasses. And then more specifically, like for any Hecker eigenclass, there should be a Galois representation, such as a trace of Frobenius matches the Hecker eigenvalues that you use. And I think I have like 3 minutes left or so. Right? 25, great. So I have like 8 minutes. Wonderful. Oops. And so the theorem is that the conjecture is true. Sorry? No, just for any torsion class, there's a Galois representation. There's also what would be called Serre's conjecture, that whenever you have a Galois representation, you can find a torsion class. But that's much harder. So that's like Weil's theorem. So let me make a couple of remarks about this and then stop with this first part. So I was stating this in the first case because there one can still draw pictures. But the same works for GLN over K, where K is any totally real OCM field. And the totally real K is conditional on Arthur's work, which is now essentially unconditional. So, I should also say that for the torsion-free part, this was proved earlier. There the result is due to Harris, Lunn, Taylor, and Soren. And following more closely their method, a student of Richard Taylor, George Boxer, announced that he can essentially reproves this result. So I haven't seen the precise theorem yet. And the last thing I want to do is I want to discuss an example. Sorry, there's another thing I want to say. So there exists a version, not just mod p, but mod higher powers of p. And this implies that one can get Galois representations, so p-adic Galois representations. For, let me just say, many automorphic representations. So Langlands conjectured, what's still on the blackboard there, that whenever you have some automorphic form or automorphic representation, you can find this motive. And so we can't construct the motive in any case. We can only currently hope to construct these p-adic Galois representations, which is slightly weaker. And this should work for all so-called algebraic automorphic forms. And currently we have to say regular algebraic, which in terms of this motive means that some of the Hodge numbers are distinct. And so, like the simplest case of a curve is somehow still open, of a curve of positive, like genus bigger than 1. And yeah. So I promised to come back to this elementary question about when a polynomial has a root mod p. So that's what I want to do now. So this example is taken from the thesis of Figueiredo from 98. So what he did is the following. So he actually started with a polynomial. Okay. And you're interested, say you're interested in the question, for which primes does this have a root mod p? So let's first analyze this polynomial. So it generates an A4 extension of Q. And it corresponds to what's called an even Artin representation. So it's precisely the case that we can't attack with current technology. Maybe in the A4 case we can, but over Q. And so also, let me say that it's ramified at 3 and 61. And so, I mean, this implies, this even Artin, that it does not come from the homology or cohomology of the modular curve. But what he observed is that you could try to find this, this kind of extension after you restrict to an imaginary quadratic field. Then some of the obstruction, this evenness which obstructs it, is not there anymore, and you can try then. And so he actually finds a 3-torsion class at the correct level. So in H1 of H3 mod gamma, Z, where gamma is some specific congruent subgroup, in SL2Z, SL2Z join I, C is 0 mod 3 times 61, and D is 1 mod 3. So you can try to guess where you should see this guy, and because it's ramified in 3 and 61, so you need to put these kinds of congruence conditions there. Oops. So whose Hecker eigenvalues, so it's an eigenclass, it's a Hecker eigenvalues. So you have some AP in Z mod 3. P here is a prime of Z adjoint I, seem to match. So you compute it. So he conjectures that some of the corresponding Galois representation should be the one for this guy, and then you can check whether numerically it works. And for the first few primes, check that there seems to be this relation. And then once you know that there actually is a Galois representation, you can check that it's the correct one. So they do match. And thus, you can state the following relatively concrete result. There is a solution to this polynomial as a 0 mod p if and only if this number AP is non-zero. All right. Right.
Do you have to go up in Galois or something to get enough?
The question was, how do I get these periodic Galois representations? And it is true that somehow I have to increase the level at P more and more to see this. AP, it's the Hecker eigenvalue of this 3 torsion class. So you have these Hecker operators acting on this guy, and they map the 3 torsion element to the same time some element in F3. And they're relatively straightforward to compute once you set this up. And so then you can easily compute these guys, and then you can check whether this has a solution or not without knowing what the solution would be. Modulo powers of P, there are many automorphic representations. I didn't say automorphic representation, I said that there are torsion classes, no? Or what? Okay, yeah. Yeah, I mean, this subgroup is expected to grow exponentially, and you just compute it in examples, and like, it's really big, and there are really big primes which divide the torsions. And so this means that the theorem says that there are associated Galois representations, so that means that there are humongous Galois representations of very, very large degree, which are ramified at only very, very few primes. And so this can't happen over Q for GL2 over Q, and this is somehow the main part of proving Fermat's last theorem, that this can't happen over Q. It's Serre's conjecture. Precisely because there's no torsion over Qs.
You might say anything about that space, I mean, about its topology.
What?
Can you say anything about the topology? Give us some idea of what the space looks like.
Well, I tried to draw a picture. I don't know if this helps. I don't know what the question is.
Well, I'm not sure how to ask the question.
Yeah. So the problem is that I'm not a topologist or geometer.
So, I'm a topologist. So
Yeah.
why the complement of the Baronian rings occurs as one of the three manifolds for this geometry.
Can you say anything about multiplicity? I mean, how often you get the same representation in the mod P class from different.
How often do I get the same Galois representation in what P class? I don't know.
I mean, the dimension of the space.
Yeah, I mean, mod P might be slightly tricky to say this.
Space of Hecker. Yeah, is that known? That it's high.
I mean, someone characteristic zero, I guess you know precisely what happens. But like with mod P coefficients, it's probably very little is known.
It doesn't axiom simply either.
It doesn't. I don't think so. No.
Do you ever, maybe this is what we do next out, do you ever use the geometry of this H mod gamma, or is it just
Do I?
the eigenvalues of vector operators on the
I don't use much about the geometry of the space.